Alright, so we're going to talk about equations of planes. So planes, again, are a three-dimensional shape. And we're going to basically try to get the standard equation of a plane, which is ax plus by plus cz equals some value d. So where a, b, and c, and d are real numbers, and x, y, and z are variables which correspond with the x, y, and z axis as we go through this. So the general idea, kind of big idea of what we're doing is we start with a plane. We'll just call it plane P to be simple. And we're going to take a known point called P naught. So in this case, A, B, and C on the plane, where we know those values of A, B, and C. And what we're going to do is pick a general point, just X, Y, and Z, that we also say is on the plane. And we're going to use some vector analysis to figure out the equation of the plane. So we're going to start with this displacement vector, which is going to be P minus P naught. And then what we're going to do is use our dot product to figure out a value that this is going to be equal to. So again, P naught, if we subtract our ordered triples, gives us that value, quantity x minus ai plus quantity y minus bj plus quantity z minus ck. Now what we need is another vector. If we're going to take the dot product, we're going to need another vector, and it's a special vector called a normal vector. It's going to form a 90-degree angle with our plane. So we're going to either be given this or define it as such so that it works. So there's our normal vector. And why it's nice is because when we take the dot product, which is the magnitudes times cosine of the angle, cosine of 90 is 0, so the whole thing is going to be 0 as we go through it. So let's look at a numeric example and see how this works. So we're going to be given something like this, where we want to find the equation of a plane that is perpendicular to this vector, 3i minus 5j plus 4k, and it contains the point 6, negative 7, negative 2. So that's what we're looking at. We're going to use the idea that we just talked about before. So we start with our point P naught, that's our known point, and we define our general point, point P, which is x, y, z, and we find the displacement vector. So we subtract those to get our displacement vector, and it looks like this. So we have x minus 6i, y plus 7j, z plus 2k. And I have a normal vector as well. So again, that's at 90 degrees, and that's been given to be normal at 90 degrees. And so I'm going to take the dot product, which is the magnitudes times cosine of theta. And I don't have to find the magnitudes because I know that that's going to be 0 because theta is 90 degrees. So the whole thing is 0. So I know the dot product is 0, and we have two expressions for the dot product. So I'm going to use the other expression to help me get my equation of a plane. So we also know the dot product equals this, where I just multiply the values, the scalars in front of the unit vectors. So I get 3x minus 6 plus negative 5, y plus 7 plus 4, z plus 2. And now what we're going to do is we're going to substitute in our value that we just figured out for the dot product before. So that whole thing equals 0. And so now we're getting really close to the equation of the plane. And from here it's just algebra to manipulate it into the form we want. So we distribute everything, and that gives us a new expression. And then we're going to combine our like terms, which in this case is just the constants, bring it to another side, and there we go. That is our equation of that plane. So any point on that plane is going to satisfy that equation. So that's given a point and a normal vector. We could also look at a problem, where I have 2 points, but I'm given the equation of a plane. So let's say the equation of a plane is given to be 4x plus 2y minus 10z is 300. And we have 2 points, but they're missing some information. So point 1 doesn't have an x value, and point 2 doesn't have a y value. But we know that they're on the plane. So we're going to be asked 2 questions about this. What's the distance between them? And then what's the z-intercept? And so the distance between them is harder than the z-intercept, so we'll do that first. Well, that's going to be the magnitude of the displacement vector. So if I subtract those 2 vectors and take the magnitude, that's the distance between them. So to be able to do that, I need to figure out the missing pieces for points P1 and P2. Well, if I know that they're on the plane and I have the equation of the plane, I can use that information. So there's my equation of the plane, and that has to work for all points on the plane. So I'm going to plug in the pieces that I know and solve for the pieces that I need. So it's 4x1 plus 2 times 4, because that's the point out, minus 10 times 5. So that all has to equal 300. If I solve it, I get x is 85.5. I do the same thing for point 2, plugging in what I know, and I solve for y2, and I get 176. Alright, so now we can figure out a displacement vector. I subtract everything, and I get this quantity. So I get this vector, it's a displacement vector, simplify it a little bit. And now I have my vector. So there's our vector, and what we want is the distance between them, so we're going to take the magnitude of that, which is our 3D Pythagorean theorem. So we just square everything and add it all up, and that gives us 189.1. So that's the distance between those two vectors. There's no units on it because we weren't given any units. All right, well, the next one is the z-intercept, which is easy. The z-intercept is where I cross the z-axis, which means that x and y are both 0. So I plug those in, and I solve for z, and I get negative 30. So my z-intercept is the point 0, 0, negative 30.